Urban is from University of Stellenbosch and Pretoria, and he has spent many years in the diamond industry, particularly in the marine field. And so with that, Urban, we look forward to hearing more about an overview of Southern African marine diamonds. Thank you.
Thanks for the introduction there. Yeah, I thought it was very funny that Mike de Wit spoke the other day about the University of De Beers. I suppose I'm the guy that's never left university, you know, I'm still there. So yeah, I'm just going to stop my video here just to make sure that the sound's good enough. So just by, there we go. Just by way of introduction, I just want to, all the images in this presentation is obviously courtesy of Deb Marine Namibia and De Beers Marine, unless otherwise stated or referenced. Yeah, I'm sure you all enjoyed Ian's talk yesterday. I mean, he really covered the tremendous history, you know, spanning, you know, well over 50 years that contributed to the success of our companies. Yeah, and there were many others that's gone before me, and I mean, it's really an amalgamation of West Coast understanding that's come together over many years that's managed to put us where we are today. The present geologists employed by these companies are also to this day working tirelessly to improve things and get the resources out of the ground. Maybe just a bit of history that Ian didn't cover yesterday. So just in terms of the company structures, so the company that mined the diamonds on the Sperrgebied coast, set up Oranjemund and up to Luderitz, was known as CDM, Consolidated Diamond Mines. That was started by Ernest Oppenheimer back in the day. And in 1990, with the advent of Namibian independence, CDM basically got reconstituted as a joint venture between the Namibian government and De Beers. Also, back in 1990, that's also the same year that De Beers Marine started offshore production within Namibian waters. So the setup at that stage was the actual diamond mining licenses in the offshore belonged to NAMDEB, and they were De Beers Marine. Cape Town was essentially a mining contractor to NAMDEB. Then in the very early 2000s, that relationship again changed, and De Beers Marine Namibia was established as a separate entity, still a partnership between the Namibian government and De Beers. And today, De Beers Marine Namibia mines the Atlantic 1 deposit as their own deposit and on their own mining licenses. So that's just how the relationships has changed over the years. De Beers Marine, we still basically provide services to De Beers Marine Namibia. The bulk of that is, by far the bulk of that is the engineering services, specifically with the import of the vessels, but I'll tell you a bit more about that. Just as an outline of my presentation, so after again getting a wonderful intro to this topic yesterday from Drs. Corbett and Dr. Ward, but I'll go through a bit of a regional setting, and then I'll just look at the marine deposits, look a bit at the West Coast stratigraphy as we understand it. I'll talk a little bit about diamond input as well. I'll speak a bit about what we believe controls their position in the offshore environment, and then I'll take you a bit through how we do exploration, how we recover the diamonds, and I'll finish off with a few environmental aspects. So this slide here is essentially, if you go and pull your geology of South Africa off the shelf there, you'll find those pictures in there. This is essentially a view. I hope you can all see my pointer. This is a view of the west coast of South Africa, but it also runs into Namibia as well. That was constructed, I think these guys all worked for Sucor during the day. And this area is essentially called the Orange Basin, situated off the west coast of Southern Africa. So the oil guys were very interested in this, and they did those very deep seismic surveys, which for some other reason are now quite unpopular to do apparently. But yeah, they did these very deep surveys. So the sediment fill is up to 7 kilometers thick within the Orange Basin. That, of course, starts off within the Waterrivian succession there in these little graben fills, and things really got going during the Cretaceous. In the whole, we got sequences running here from the Albian to the Cenomanian. That's quite a thick sequence. There's a big unconformity or major sequence boundary in 93 million years. And then the next package, still in the Cretaceous, is the Santonian up to Coniacian package. Then there is a seems to be a slight decrease, or in this section, and that could be, I was going to say, a combination of the taps being turned off up until we reach what is in old days they termed the Cretaceous tertiary boundary. I suppose today that would be the Cretaceous Paleogene boundary. That's the new nomenclature. But so that sequence of events was characterized by a very wet phase between Gondwana breakup and the main deposition of sediments within the Orange Basin. What we see, these things are being made up. It's mostly fluvio-lacustrine sequences, and as we encounter it today, it's essentially clays and what used to be sands, but it's now sandstones. The boundary between the Cretaceous and the Paleogene sediments is essentially an erosional unconformity. So post deposition of this sequence, there was quite a bit of uplift that happened here, and this tilted the Cretaceous strata. So they're slightly dipping offshore, and obviously we suspect there's quite a chunk of Cretaceous that got eroded off again. And as John pointed out yesterday, we don't really see the Cretaceous onshore, but there's a very good chance that there must have been something there at some point. Going into, so that the next phase of deposition, and that's really that little slither here, which is now the tertiary sitting on top. So on the actual shelf, on the actual continental shelf, there's actually very little tertiary sediment. It seems to have gone over the shelf edge and into the deep water and into the abyssal plain. I'll give you a bit more of an overview of that just now as well. But yeah, there's essentially a depositional gap there that ranges from the Paleocene right into the Eocene. That's stretching roughly from 67 million to 42 million years, where there's this big gap. And then from that we have mostly Eocene going into Miocene deposition that we also see on this shelf edge. but yeah, that's the very deep view of where the oil people obviously look deeper. We're interested in the surface over here, where that little arrow is, it says alluvial diamonds. And this is another view of the Orange Basin. Again, you can see the west coast here on the onshore and on the offshore side. That is a bit of a bathymetric map. And in this thing has been divided into, these are the concessions that you see here, that's like the official diamond licenses that things have been divided into. So on the South African side, you can see there's the Namibia-South African border. So things get done differently north and south of the border. On the South African side, I mean, what's called the A concessions is literally from the waterline to 1 kilometer offshore. The B concessions or inner shelf is up to 70 meters below sea level, with the middle shelf 70 to 200 meters below sea level. And then there's also, of course, the D concessions that go from 200 to 500 meters below sea level. On the Namibian side, so there is the big Atlantic 1 mining licenses. That is the main operational area of De Beers Marine Namibia's production. Just again, a bit of scale there. At Atlantic 1 is from parallel to the shoreline, that is just over 100 kilometers long. And it's about from inshore to offshore, it's about 50 kilometers deep. So it's a fairly large area, it's a very, very large area. So typically we would, oh no, let me just finish on that. So then in the Namibian waters, that's that sliver, of course, between the Atlantic 1 or the middle shelf, as we call it, that is known as the midwater, generally called the midwater, and they are usually associated with these, or traditionally they were part of the actual onshore licenses as well. And then there's this whole group of smaller prospecting license that was declared to the offshore and to the north of Atlantic 1. That is still delineated there. So just again, in terms of the morphology of the shelf, obviously we step here from, we've got Proterozoic rocks onshore, Proterozoic and older than Namaquarant rocks onshore, and obviously you guys know what the topography looks like. You know, you've got the Great Escarpment there, but the moment that we get onto the shelf, things tend to flatten out when we start getting onto those Cretaceous and Cenozoic sequences. The topography looks totally different. So just to put it in a bit of perspective, note the inner shelf. If you start swimming directly from shore and you swim into the sea pool or walk on the seafloor, that would be cooler if you could do that. The first 20 kilometers out, you would be in 100-meter deep water. So that is about 5 meters per kilometer change. But the actual middle shelf, and that is from 20 kilometers out to 150 kilometers out over here, the change in water depth is an additional 100 meters. So that is 75 centimeters per kilometer. So this thing is essentially fairly flat and featureless. That's just something to keep in mind. I'll maybe talk about that a bit more later. This is my version of a map that John Ward already showed, but mine's got a few funky animations on it, so you absolutely have to look at this as well. So on this map, you can see the purple diamonds are all the group 1 kimberlites, and the orange diamonds are all the group 2 kimberlites, or the orangites. sitting there. The red circles delineate diamond clusters that are economical. So we can see quite a few of the economical diamond clusters on or close to the boundary of the Orange River drainage basin, which covers the majority of Southern Africa. What we essentially have is what we call a source conduit and sink relationship. So moving the diamonds from onshore and into the ultimate sink, which is the Atlantic Ocean. My little yellow line here, what I'm trying to present here is, if you just look at it from an offshore perspective, as far as I know, the first offshore diamonds are basically where guys mined it in the sea. There's an operation here just north of the Olifant River called the Punt, where the guys were diving. And then all along the Namaqualand coast, there has been sporadic activity in terms of mining. Of course, going into the Namibian sector of this, things really heat up. And I think the furthest north that was really exploited economically was at a spot called Hottentots Bay. Obviously, there are still occurrences going all the way up, but that's kind of the main area of where you'd find the most diamonds within the sea, and it is a big enough area. It's certainly not too little. Also, just to look at things in a bit more perspective. So now I'm looking at that sector of the Namibian diamond megaplacer. Again, this is a diagram that's been put together by my predecessors, and it's a neat illustration of the various expressions of the deposits that we find. So we have the Orange River, the fluvial meanders sitting here. I'm going to talk more about the fluvials a bit later. We have the mining area 1 Uranium linear beaches going into the pocket beach environments, going into the Aeolian deflation basin, and then right up there that is Elizabeth Bay, where Elizabeth Bay mine, where the Aeolianite was essentially exploited for diamonds. And then directly offshore of the Orange River, we have the Atlantic 1 marine placer situated there, which will tell you a lot more about. Maybe, yeah, so just as a summary of this, the diamond placer in Atlantic 1 was formed during several episodes of deposition. It was a multiple deposition episodes and multiple episodes of reworking from the Paleocene onwards, with sea level rises and rising and falling due to the influence of the glaciations. And this all happens on a buoyant shelf setting, which I'll talk about as well a bit more later. So just as you can remember, a few slides back, I talked about the real shallow water stuff. So I thought we should probably start there. So the real shallow water, less than 30 meters, that's the realm of the small scale diver operations. So there's a couple of, I think there's a divers in Lüderitz. There's a whole group of divers in Lüderitz, and they operate from there mostly to the south these days. But there's also divers operating out of Alexander Bay and Port Nolloth. These guys, as I said, it's very much small scale operations. They look for trap sites and gullies and channels along the coast. I particularly like this image because it shows you the onshore aerial photograph of this. I think this area is called the Hook. You can see a drainage channel onshore and on the offshore. You can see this same structural textures that you see on onshore repeats on the exposed bedrock offshore, and that channel gets followed offshore. And this is a photograph of a little vessel called the Rachel, situated in this area called the Hook. This image, don't be fooled by this image. This is a beautiful calm day on the west coast. The wind was born near Luderitz, so it's most times a fairly hostile environment. So on average, the diamond divers can only dive for 50 days in the year. The rest of the time, they're essentially waiting on weather. So it's a tough business. I mean, a lot of guys tried in the past. It sounds glamorous to go diving diamonds, but I can assure you it's not by any means a way to get rich quickly, and it is hard work. So it's quite a tough hands-on end of the business. The next step down is what we call the midwater, 30 to 70 meters is typically within in the Namibian water, what we refer to. And that is where, as we've heard yesterday, that's pretty much the kind of midwater settings, and where these big channels were found in these midwater settings. That's pretty much where Samming Collins and the MDC, that's really where they got going, and in the 70s. As you can see here, this is just a side scan sonar image that this lady called Megan Runs did a very nice MSc on that recently. So you can see that kind of Neoproterozoic basement structures with little channels in the gullies and the structural features. That's still very much evident in the offshore environment. There's been a lot of different companies and operations that worked in the midwater in the past. Some of them, or most of them, has pretty much come and gone. But I just wanted to show this image. It's also a Cape Town-based company called IMDH. They have this vessel called the Explorer, which is also a diamond sampling plant. They still seem to. It's essentially, along with De Beers Marine, they are the other guys at the moment that seems to be active and make a living in the slightly deeper water settings. If there's anybody else out there, I'd like to hear from you. Yeah, but they actually did some sampling here with that vessel in this area that I'm showing you in this image. So yeah, so that's the midwater setting. So then on the middle shelf, what we call the deep water deposits, typically between 120 and 140 meters. We're not on the Precambrian basements anymore, so no more bedrock and gullies and things like that. We are sitting on Cretaceous Cenozoic footwalls, which is a lot more smoother and undulating. And the coarse gravels are found here, and they are located in fixed and mobile trap sites in this middle shelf setting. This then is, of course, the mainstay of traditional De Beers Marine Namibia, De Beers Marine production. So just maybe a bit on the image here. This is a bit of a cartoon image of not what it looks like everywhere, but certainly some portions of the middle shelf. So those are the cemented Cretaceous units, which we call the Cretaceous reflectors. There's a lot of vertical exaggeration here. Those things dip half a degree to 1 degree, so they're not sitting at steep 45 angles, but we tend to look at these things in big vertical exaggeration. So what we essentially have forming is a gravel lag. So we don't have drowned beaches. It's essentially a reworked gravel lag that's sitting in the middle shelf. And that lag is composed of terrigenous clasts, in other words, the rocks that got washed down the Orange River, the quartzites, and then locally derived. As these Cretaceous units get eroded, they generate what we call sandstone slabs, which is flat pieces of sandstone, which is also something to contend with. And we get different types of, we don't just get clay footwalls, we also get sand footwalls and conglomerate footwalls. So there is quite a bit of variation in there. Maybe just also good to mention at this stage, we tend to talk in the path of, oh, we mine in the deep water, but keep in mind it is 120 to 140 meters. It is on the middle shelf. It's not in the abyssal plains. The guys going for these, that wants to go and mine these seabed nodules, I mean, they're looking at 2,000 meters down. That's a completely different setting and ball game to essentially what we are familiar in operating with. It's just a couple of views. So these are actual images of what the gravel lag looks like. So this is a side view of a sampling hole. There's a scale there, so that's a 50 centimeter scale. So those very, very hard Nama quartzites that John spoke about yesterday, that destroyed all the poorer quality diamonds and only delivered, ensured the survival of the best quality and the most hardy diamonds. That's them there. And there is an actual piece of the Cretaceous clay footwall sticking out. This is a nice, these two photographs are nice, clean examples where we can see clear, just the clear gravel horizon. I mean, that's literally our ore body. But sometimes it can be covered with shell or Holocene mud overburden. And then we also get these, I've already spoken about the sandstone slabs. That's just another view of one of those from what you see on the seafloor. Of course, at 120 meters, things are pitch black. So if you want to take photographs, you've got to turn the lights on in order to see these things. And all of this rests on obviously the footwall stratigraphy. So that's, I need to drink of water. So this is a map that was put together by some of our co-workers most of this work was done in the 1990s as lots of biostratigraphy and vibrocoring and geophysical surveys conducted to put this together. So, but what we essentially see is in this broad view, so there's still this thin slither of Precambrian rocks right to the inshore, and then we have a bit of a there is a little bit of Paleogene sediments there, the Eocene and sediments is sitting there. There's actually a section of it in Atlantic 1 to the north of Atlantic 1, but very limited down in the Southern African Sea areas. And then the thin but very much extensive going over the shelf cover of Miocene sediments. That's just, again, a bit of a cross section there. Again, note that so the scale there, so between that's -50, that's 150, that's 10 kilometers. So this thing is actually as flat as the Free State. We just put a lot of vertical exaggeration in so that we can see what's going on. So there you can see what the succession looks like. Most of it is Cretaceous, and we have these almost slithers of Eocene clutching to the Cretaceous sequence. We see a clastic Miocene portion that towards the offshore goes into a more biogenic Miocene section. And it's essentially almost want to say between the inshore bits of the Miocene to where this Holocene mud starts. That's essentially the main areas where the mining on the middle shelf has been focusing. As I've mentioned, in the South African sector, we mostly sitting on these Cretaceous sequences, and these are reflectors, or we see them in our geophysics, and they are neat to go and map out because they kind of make a bit of a riffle board effect as well that assists with the concentration. Towards the inshore, there's what we call the mud belt. It is a pile of Holocene mud. At some point, that thing actually becomes, there's gas in there as well. So it's at about 20 meters thick. We can't see through it with our seismics anymore. So there's a bit of a blanking going on in the center of it. So it's a bit of something to contend with, but at this stage, that thing is in our way. It's by no means mineable. So that's just serves, so that's what serves to the footwall of our ore body, which is this extensive gravel lag drape that is sitting in Atlantic 1. I promise I didn't put these slides in yesterday. I put them in a couple of days ago, but they were quite the discussion yesterday, so I thought I'd just keep them in. So Dave Phillips did work where he basically dated argon inclusions, CPX inclusions. He dated them using argon. What that does, it doesn't give you the date of the age of the diamond. It gives you the emplacement age of the diamond. So when that thing gets in place, that argon gets reset or something like that. And so that gives you an idea of when those diamonds were in place. So and there's Mike DeWitt's original Karoo-Kalahari River diagram at the bottom here. So the Namaqualand sector diamonds, which we've long suspected came down the Karoo River. It was quite neat because, yeah, Dave Phillips pinned these down quite rightly. He says the age ranges, you can see that baby blue graph that represents the Namaqualand diamonds. I'm not sure why I put a RAPA on top, maybe because he just wanted to show it in contrast to something else. But he basically said there's 100 to 300 million year. That's the age ranges for the eruption of those diamonds. And yes, and then he blamed the group 2 kimberlites and the Jeanning age kimberlites for the source of these diamonds. He saw a very limited contribution from pre-Dwika or Cretaceous group 1 kimberlites to the Namaqualand population. Dave subsequently did more work, which he presented and published at the Kimberlite conference in 2017. I think there were uncertainties around specifically with the ages that he got from the Namaqualand diamonds. There was some technical issues that he had with his initial 2008 work, and I think he just firmed up on that. But his initial findings didn't materially change from what he saw in 2008 or presented in 2008. If we look at the Namibian diamonds, which I've also had a look at, so he got quite a bigger range, but he said the majority of those are from kimberlites that's younger than 240 million years, and that includes the Cretaceous group 1 Kimberley pool kimberlites, and a little bit of the group 2 as well. He did say that less than 10% are older than 400 million years, thus limited pre-Dwika contribution, but not no pre-Dwika contribution. There is a little bit of a signature sitting in there. So yeah, just to reiterate again, yeah, there is a fundamentally different. We simply have a Namakwa megaplacer and a Namibian megaplacer, of which the Namibian megaplacer is by far the big brother in the relationships. Other slide that I to look at. Again, the Orange River is quite a neat thing for us to look at, because it is a very well-preserved record of diamond deposition through time. So we do recognize, at the very least, we do recognize gravels in Atlantic 1 that we think are of pre-proto and proto and meso ages. But we need to look to the Orange River if we want to get a feel for when those depositions happened, because it's all mixed up in the offshore because of all the reworking that's happened since. So yeah, so that's just the story that we see from the Orange River. Starting out, you know, the first stuff coming down in the Eocene stone sizes, gradually increasing as things get younger, with a peak of diamonds, or the main slug coming through in the Oligocene. So that's important to get a grip of the timing of your input on the shelf as well. It's important to understand that for exploration purposes as well. The other thing, which is of course quite handy, the guys onshore love to look at their exotic clast assemblages to basically fingerprint the onshore deposits, and lo and behold, we do get all the stuff that they get along the Orange River. We see all those clasts in the offshore as well, very, very nicely. So also a useful thing to look at is your clast assemblages. And then, of course, the other thing which is important in the offshore environment are the morphological control. Again, just briefly, the images that we see here, that's a bit of an air gun section. Of course, again, that's wildly exaggerated, but yeah, we can see where sandstone platforms and where there's a bit of gully and edges and things like that. Again, yeah, this is the bottom image, which is also eminently useful, is a swath bathymetry image of the seafloor. The way that we do the coloration on these is again, just brings out even the most subtle changes. But there, for instance, seems to be quite a bit of a scarp edge around here and surrounding a depression. But these things are, we're only talking about a meter there. So it is very subtle, but it's very important to understand the subtle yet important changes in seafloor morphology that does influence your mineralization quite a bit. And yeah, again, repeat the repeated marine transgression there. As we move throughout up and down the coast, there's quite a lot of variability in footwall and gravel composition. So you have to keep your wits about you because of the rapid changes that happens over relatively short distances. But despite of all those things, the biggest challenge still remains the fact that these deposits are covered by a lot of water and you can't see what you're doing. So just want to touch a bit briefly on how we do marine explorations. So mostly in the 1990s, we had our own survey vessel, and we did quite a bit of survey, towfish surveys, and boring. And in Macmillan, it's useful to have the Jago submersible to go and directly observe the seafloor. Ian also spoke about this yesterday. That's still it was the autonomous underwater vehicles. These things were breakthrough 20 years ago, and we still use them today. they give us very high resolution swath bathymetry, very high resolution side scan sonar, and even this day we collect 3D survey, which is literally a cube of sub-bottom data that you can slice and dice in 3D space. So quite neat tools that we have available these days to assist us in unraveling all that goes on the seafloor. Sampling vessels, we've had quite a number of them through the years. Again, I'm not going to go into the history. This is the current sampling vessel that the De Beers Marine Namibia operates in Atlantic 1. It's called the SS Njoma. It was commissioned in 2017. It carries a 10 square meter seabed tool that gets lowered through a moon pool in the center of the vessel. It lands on the sea floor. They start drilling and they pump the material up, and there is a DMS sampling plant that does a very neat job of batch processing these samples. And we have a whole lot of these 10 square meter samples that gets used by the geostatisticians to generate a 100 by 100 meter blocked resource that subsequently gets sequenced for exploitation. This is the, as I said, the Atlantic 1 diamond recovery fleet. So at the moment, there's 7 vessels out there. They are roughly arranged. These two on the left-hand side were the first ones that was introduced, and they were steadily followed by additional vessels, and right up to our latest vessel, which is the Benguela Gem that entered service at the beginning of this year. We generally refer to them as drill ships and crawler ships, so the two categories of ships. The drill ships, they employ what we call the vertical recovery method. So it's essentially a very large disc that gets deployed through the moon pool. This turns and sucks at the gravels on the sea floor. In the case of the drill ships, they use airlift, which the material gets transported by the injection of air at the bottom of this tower, and then goes up to surface. Again, goes through a DMS recovery at surface. Once that circle has been excavated, they lift it up and then they move to the position next door. There's been quite a bit of progress through the years. That was the original Worth drills, as we used to call them. But today we use a new animal which has actually got moving parts in it and is better at cleanup efficiency. So that's been developed. That's been developed in-house to improve on that technology. Oh yes, they are, in terms of how fast they can mine, they are slower than the crawler ships, but they do work in rougher terrain. So there is a bit of a horses for courses going on there. The crawler ships, this is what we call a horizontal recovery method. So you have a crawler tracked vehicle. Yes, there's the picture. This machine is a monster. It's from its tracks to its top, it's 8 meters high. And it's got this long elephant trunk in the front that slews from side to side, and while the vehicle tracks forward, and that way it recovers all the gravel. What's neat about the crawlers are they use a pump. They don't use airlift, and if you pump, you can typically move more material to the surface. Just a bit on how these vessels are operated. They are at sea for about 2.5 years, and then they come for import maintenance. They come here importing in Cape Town, and then we have literally thousands of contractors that crawl all over this vessel and fix everything that needs to be fixed. They typically, once they're out at sea, though, they typically operate 24 hours, 7 days a week, 365 days a year. Refueling gets conducted at sea, fresh water gets produced on board, There's a launch that brings supplies and takes away the garbage back to shore, so nothing goes into the marine environment from that perspective. These vessels are crewed by roughly 60 people that work 12-hour shifts, and every vessel has got 2 crews, so every 28 days the crews rotate. So that's roughly over 1,000, just over 1,000 people that works at sea, and then we're not even talking about the number of staff that works onshore. Also, everybody that works at sea, the mining and the plant systems are highly automated. So everybody that works at sea is well skilled. So it's a highly automated handoff and skilled operation. Just a bit historical production. So De Beers Marine started in 1990. I think the very first year's production was something like 25,000. This year, and especially with the introduction of the Benguela gem, the De Beers Marine Namibia aims to produce well over 1.5 million carats. The 1 million carat mark was first passed in 2006. And this was driven largely by the introduction of additional vessels, but through the years, there was a lot of initiatives to increase the rate of recovery by tweaking these machines and doing continuous improvement on the way we operate and the technology.
5 minutes, please, Urban. 5 minutes.
I'm almost done. So there's been a lot of advances through the year, and so that's just what I'm basically trying to show you. So even though the recovered grade that got mined dropped off quite significantly as time progressed, the increase in rate at which those grades were recovered offset that to such an extent, and I think that's a key part to the success of the marine operations, the ability to do that. Just De Beers Marine did have a go at mining in the South African sea areas, but that was terminated. I mean, it is certainly more challenging working in the South African area, but that was roundabout just the fallout from the 2008 banking crisis. I mean, we were hit very hard in 2009. The whole diamond market went off a cliff in 2009. De Beers had to make some very hard choices back then. So, and then that project was terminated. Just finally, this is my last slide. Just a word on the environmental side of things. So the De Beers group of companies run rigid environmental systems. We use ISO 14001. And the first impact assessments were done when mining started. It was a big impact assessment that was done in the early 90s. And it's been from that baseline, that's been continuous. I mean, every year there's ongoing research and monitoring just to investigate what's the natural variability, what's the impact on the environment, and how fast do things recover. So essentially, I mean, when we mine these diamonds, everything gets treated on the vessel, and apart from the diamonds that we recover, everything else gets returned into the mine out areas. The second thing that is important to remember, I mean, these deposits don't get mined from one side to the other. It is quite scattered and quite selective, the areas that get selected for mining. So it is, in a year, it's a very, very small area that actually does get impacted. And the repopulation of marine species, once we move away, they naturally over a number of years return and repopulate those areas. And that's the end of my presentation. Thank you very much.
Thanks very much, Urban. That was a really interesting look at how mining is done offshore. Do we have any live questions? I see there are a few in the chat, but in the meantime, does anybody have a question for Urban?
Yeah, just to kick off, Urban and Lyndon, I think you're on. It's fascinating you say that you mine, I guess, selectively, and I guess, you know, it's what the alluvial or land-based alluvial businesses also moved to, you know, where obviously the key thing that you're doing down there, and it may be even easier underwater than on land, you really get to understand your ore body well. And I've seen some of the MS or some of the theses come out of work on that Marine One platform. You know, the geology is amazing and the level of work and detail is fantastic. So, you know, you guys certainly should be proud of the work you do on that 120-meter beach. Mm-hmm. So, Lyndon, are you more relaxed about your approach now?
Yeah, okay. I think maybe, John, if I can just comment on that, what makes the I mean, what makes the setting unique, you have a floating production unit, and on the seafloor you have a giant blanket of a deposit. So the nature of it is such that you can access any part of it at any time. So so yeah, you can, and that's where the great understanding of it comes in handy, because you can pick better.
And please, before we go to the other ones, just tell us what's the age of that 120-meter beach, drowned beach?
No, it's not a beach, John. It's a lag. It's I mean, as I said, I think what we are seeing there, as I showed there, we kind of like looking at the Orange River because we do see a clear link there, and it's essentially what was debauched by the Orange River through time onto the middle shelf has been redistributed by the transgressions, and yeah, that's essentially what we see. So yeah, the same ages as we see onshore, we could have had contributions sporadically from the Eocene onwards.
Yeah, but I mean, the great thing about it is, and you've commented on that, is how flat it is. I mean, obviously it's got boulders and rocks, but it's superbly flat, which helps the mining.
Yes, it certainly does. I can quickly. I see there's two questions in the chat box. Can I quickly answer those?
Yes, please do.
Just to answer Mike Lynn's question, I don't know what the life of mine is because we don't know what the edge of the deposit is. I mean, it doesn't work, and I know it freaks the kimberlite guys out, because that's the first thing they want to know is well, how many hectares is your kimberlite? You know, we simply don't know how big it is. So yeah, we'll just carry on. COVID was interesting. It was also very difficult. With the vessel operations, the crew had to go into quarantine. So you got locked in your hotel room and tested regularly for 7 days, and then we created a biobubble and put everybody on the vessel. But it was quite challenging.
There are a couple of others there as well. Sean Johnston asks, have there been any offshore diamond recoveries related to Volphus Ridge in northern Namibia in relation to natural traps?
Not that I know of.
And you might just add, Urban, that as you go north, and John did allude to that, you know, your diamond size gets really small.
Yes, yeah. I'd be very surprised if someone finds something there. Then in terms of what's the lifespan of the deposits? Well, I already gave an answer on that. I'm afraid that depends. And then, yes, this is the only location where diamonds are mined offshore. And I know the Russians might have looked at their stuff in the past, but I really don't know anything about that.